So coming to the next question, 13th one. Some of the silent features of the 741 op amp are listed below. High power consumption. So the first point is that operational amplifier will not take the high power consumption. It will take max to max 12 volts. Okay, plus 12 volts here, and here it is minus 12 volts. So it is a wrong thing. The external frequency compensation. That means we observe the active filters where the low pass, high pass, and band reject. So based upon the external components what we are connecting, the resistors and inductors, the frequency of the operational amplifier can be changes. So if you take the low pass filter, with the help of a resistor and capacitor connection, we can make allow only the low frequencies, and with the help of high pass filter, so with both R and C connections, we can pass only the high frequency component. Similarly, band pass and band reject. So from this concept, what we can able to understand is that by making the external connections, we can make the frequency compensation. And latch up is not provided. Latch up happens in the what we call silicon control rectifier, that we will see the next. So no latch ups happens in the operational amplifier. And next one is the offset null capability. Offset null capability means if you take the operational amplifier, let's take it is V1, V2 and V0. So if V1 is 4 volts and V2 is 4 volts, then V0 must becomes is equal to 0. Fine. So if V1 is equal to 0 and V2 is equal to 0, then V0 must becomes is equal to 0. That means if the input voltages are same, then the output voltage must be 0. Why? Because operational amplifier output voltage can be given as V0 is equal to some gain into non-inverting voltage minus inverting voltage. Okay, it is the output voltage formula of the operational amplifier. Whenever the both the two input voltages are same, then v1 minus v2 becomes is equal to 0, then a into 0 becomes is equal to 0. That means the output voltage becomes is equal to 0. But instead of getting the 0, we will get some maximum voltage, that we can say with respect to the schematic diagram of the operational amplifier. So if I'm giving the 4 volts here and 4 volts here, actually we're expecting the output as a 0. So based upon this concept, but it is the ideal case only. While coming to the practical case, we're getting some non-zero voltage at the output side. So why it happens? Because here the differential amplifier is the starting stage of the operational amplifier. In the differential amplifier, we are using the two BJTs. So this 4 volts is goes to the base of one BJT, and this 4 volts is goes to the base of the another BJT. So both the two BJTs must not be identical. So what happens is that if I'm giving the, for example, let's take, if I'm giving the 4 volts here, if it enters into the BJT2 base, then due to some drop, this 4 volts may be converts into the 3.9 volts. So here if it converts into 3.9 volts, then what it reads is that V0 is equal to gain into 4 minus 3.9, right? But because the one is 4 and the other one is the 3.9, but actually I'm giving the 4 volts, but it is taking, due to the internal drops, the BJT2 is taking this 4 as a 3.9 volts. Then automatically we will give the, when this operational amplifier will give the huge output voltage, right? So in order to avoid this case, how much amount of drop is happening here? 0.1 volt of drop is happening. So what I'm doing is that I'm connecting the 0.1 volt voltage source here, and then we have to apply the voltage here. So now if I give the 4 volts, then this 4 plus 0.1 becomes is equal to 4.1. This 4.1 goes to the second transistor BJT. Anyhow, it makes the 0.1 as a voltage drop. So then the 4.01 becomes to 4 volts. So now 4 and 4, now you will get the exact 0 voltage. So in this example, whatever the voltage we are additionally connecting here other than the input voltage, this voltage is just to make to output as a 0 if the both the two input voltages are same. So this is called as a offset null capability. Offset null capability, this concept is. So this offset null can be do with the help of this operational amplifier with the help of one extra supply. Fine. So it, and whatever the voltage source we are connecting here to make the output voltage as a 0 for the same inputs is called as a offset voltage. Fine. So the operational amplifier is having this offset null capability. So totally external frequency compensation and offset null capability. So B and D are the correct answer. So fourth option is the correct one. It is the 13th question. And while coming to the 14th question, So in this question, what is the output voltage of the following circuit? So we have to find out the output voltage for this given circuit. As I told that here the input voltage is here, the two input voltages are there, VA and VB. And if I consider this op amp as an ideal, so here and here the same voltage maintains. Let's take here V1 and here also the V1 maintains. And consider some current I is coming here. Let's take it as I1 and here I2 is coming. And this I1 current is flows through here also. And here this I2 current is also flowing through this 20 kilo ohms. Why? Because the current flowing both these two terminals of the operational amplifier is 0 due to the infinite input impedance as the case of ideal op amp. So now I1 is equal to I1. That means the current flowing through this 20k becomes is equal to current flowing through this 100k. That means VA minus V1 divided by 20k is equal to V1 minus V0 divided by 100k. So kk gets cancels, 0 0 gets cancels, and 2 then 5 times. So now do the cross multiplication, then it becomes 5VA minus 5V1 is equal to V1 minus V0. And from this case, 5VA minus 6V1 is equal to minus V0. Fine. So let this equation be like that. Now we will go to this one. So VB minus V1 by 20k is equal to V1 minus, anyhow it is grounded here. So V1 minus 0 divided by 20k. And from this one, 20k gets cancels. So VB is equal to 2V1. Fine. So I got the VB is equal to V1, and from this one V1 becomes is equal to VB by 2. Substitute this V1 as a VB by 2 here. Now finally 5VA minus VB by 2 is equal to minus V0, and here 2 3s are 6. So finally V0 becomes is equal to minus 5VA plus 3VB. Fine. So minus 5VA plus 3VB. That means fourth option is the correct one. It is a way of solving such type of problems. And coming to the next 15th problem. Thermal runaway in a transistor biased in the active region is primarily due to. So thermal runaway happens. Thermal runaway leads to self-destruction of the transistor. Actually, thermal runaway leads to increase in the temperature first. If the temperature increases, then the reverse saturation current increases. If the reverse saturation current increases, then the IC, that is collector current, also increases. Why? Because IC is equal to beta IB plus ICO. Fine. Or else you can given that beta IB plus 1 plus beta into IC BO. Okay. So it is what I explained in the lecture of this one, transistor. So it is a chain. If temperature increases, then the reverse saturation current increases. So here change in reverse saturation current due to rise in temperature. That means option D is correct one. So that is the primary reason actually. So that means the fourth option is the correct one. Right. And coming to the 16th question, here we have to match up with the input impedances. So if you see the BJT, out of all these things, it is BJT, MOSFET and JFET, and it is MESFET means metal semiconductor field effect transistor. Okay, metal semiconductor field effect transistor. So BJT is having the least input impedance out of all these three, and the next one is JFET. So JFET is having the 10 power 8. And coming to the MOSFET, that means A matches up with the 4. So A matches up with the 4 means the 1 and 4th option is there. And while coming to the JFET is having the 10 power 8. That means the C matches up with the 3. That means obviously the 4th one is the correct answer. And here the MOSFET, this matches up with the greater than 10 power 10. And why? Because the MOSFET input impedance is greater than, huge. It is in the range of mega ohms. And coming to the MESFET, it is still more high, that is 10 power 12. And coming to the 17th one, so actually here the open loop voltage gain, that means A is given as 2000, and the noise level output without feedback noise level output without feedback is 1 or 2 millivolts, and if the feedback is beta is equal to 1 by 40, what is the noise level in the output? So generally in the operational amplifier, the noise level can be decreased. So in the feedback concept, I said that if the decreasing is there means, then how much part it will decrease? 1 plus a beta, right? And that too, it is saying an amplifier, right? Operational amplifier, generally we are using the negative feedbacks here, but because in the operational amplifier, if you are using the positive feedback, it leads to an oscillations, right? So here the negative feedbacking means here we will get the plus. If positive feedback means we will get the minus here. Anyhow, so it is the expression. So now noise with feedback is equal to noise without feedback. Noise without feedback is 102 milli divided by 1 plus A, that is open loop gain, 2000 into 1 by 40. So that is 102 into 10 power minus 3 divided by 1 plus 0 gets cancels, so 50. And that implies 102 into 10 power minus 3 divided by 51. So here 102 by 51 millivolts. So 102 by 51 means 2 it is, so 2 millivolts. So here the correct answer is the second option. So it is a way of solving such type of problems. And coming to the next problem, which of the following components are used for bias compensation in transistor circuits? So we observe the different types of biasings in the transistor. So different types of biasings means self-biasing, fixed biasing, emitter biasing, potential divider biasing. So in all the biasings, what we saw is that with the help of resistors, right? So if it is a potential divider biasing, then it just looks like this, right? So with the help of resistors, we compensated the biasing thing. So that's why here a combination of resistors is a correct answer out of the given options.